Have you ever stopped to think about what a computer really sees when you type a message or save a file? It's not letters, it's not numbers. It's a secret language. And today, we're going to decode it.
Okay, let's kick things off with a little mystery. Imagine we just pulled this string of data off a corrupted hard drive. I mean, at first glance, it just looks like a bunch of random letters and numbers, right? Hexadecimal gibberish. But what if it's not? What if there's a message hidden inside?
And that's our big question for today. How do we take something that looks totally cryptic and turn it into something that actually makes sense? Well, to crack the code, we first have to understand the language the machine is speaking.
See, deep down, at their very core, computers are actually incredibly simple. They only understand two things, on or off, 1 or 0. We call this binary, and while it's absolutely perfect for electronics, for us humans, it's kind of clumsy.
I mean, just look at this wall of ones and zeros. That's just a single location in a computer's memory. Can you imagine trying to read or write this stuff all day? It would be a total nightmare. There has to be a better way.
And here is that better way. This beautiful, compact thing on the right is hexadecimal, or just hex for short. Think of it like a human-friendly shorthand for binary. It's a base 16 system. And the magic is that each hex character represents exactly 4 binary digits. It turns that unreadable mess into something a programmer can actually work with.
So, great. We can represent big numbers in a compact way. But how does that help us with, words, symbols, even emojis? What we need is a standard, a dictionary that maps all these numbers to characters.
And the first big standard for this was ASCII. It was cooked up back in the 1960s, and it gave a unique number from 0 to 127 to every English letter, number, and punctuation mark you can think of. It was basically the Rosetta Stone for the entire digital age.
Now, what's really amazing is how elegant ASCII's design was. Just look at the binary for an uppercase A versus a lowercase a. See that? They only differ by a single bit. That wasn't an accident. It was a brilliant hack that let computers switch text from upper to lowercase almost instantly, just by flipping one tiny bit.
But you can probably see the problem here. A 128-character set is fine if you're only using English. But the internet is global. What about characters with accents, or entire alphabets from other languages? And of course, what about the most important characters of all, emojis?
And that's where Unicode comes in. Now, Unicode wasn't just a bigger list of characters, it was a whole new philosophy. It separated the idea of a character, like the concept of the letter A, from the actual bytes used to store it.
The most popular way to actually encode Unicode is something called UTF-8. And its genius is this variable length system you see here. If it's a regular English letter, it uses just 1 byte, which makes it totally backward compatible with old ASCII files. But for other characters, it can stretch to use 2, 3, or even 4 bytes. It's efficient, it's flexible, it's pretty much the perfect system for the modern web.
Okay, so we know how to represent characters. Now for the last piece of our puzzle. How do we actually manipulate this data at the lowest, most fundamental level? For this, we need to put on our hacker hat and learn how to operate on individual bits.
Our first tool is the bitwise AND. The best way to think of this is like a filter or a mask. You lay it over some data, and it only lets through the bits that are a 1 in both your data and your mask. It lets you perfectly isolate one specific part of the data to check if a setting is on.
And its partner is the bitwise OR. This one is all about combining things. Imagine you've got a row of light switches, and you want to make sure one particular switch is on without messing up any of the others. OR is how you do that. It flips that one switch on and leaves all the others just as they were.
Now, I know these might sound a little abstract, but this kind of bit magic is the engine behind so much of what a computer does. Setting file permissions? Check. Defining the exact color on your screen by packing red, green, and blue values together. Yup. And that clever ASCII case-changing trick we talked about earlier? That's all powered by these simple, lightning-fast bitwise operations.
Let's look at a classic example to make it really clear. File permissions. Each permission, read, write, execute, is represented by a single bit. So, as you can see here, if you want to grant both read and write access, you just combine their binary values using a bitwise OR, and you get a new number, 011, that neatly represents both permissions at once. It's incredibly efficient.
All right, we have our toolkit. We understand hexadecimal, we know about character encoding, we've got our bitwise operators down. It's time. Let's go back to our mystery and finally crack this code.
And here it is again, that same string of hex code that looked like pure gibberish just a few minutes ago. But it doesn't look so random now, does it? You can see the pattern. You see those pairs of characters, and you know those pairs probably represent numbers, which means they represent letters.
And the process is actually really simple. First, we just break the string up into 2 character pairs. Let's start with 41. Next, we convert that hex number into a normal decimal number we can understand. 41 in hex is 65. Finally, we just look up 65 in an ASCII table, and what do we get? The character A. We just keep doing that for every single pair.
And there it is, our string of gibberish decodes into a pretty powerful and famous quote. The secret was there all along, hidden in plain sight, just waiting for us to learn the language of the machine.
But here's the real punchline. This wasn't just about solving one little puzzle. The process we just walked through, translating a bunch of numbers into meaningful information, that is the fundamental secret behind literally everything you do with a computer.
That emoji you just sent? It's a 4-byte hexadecimal number being decoded. The colors popping on your screen right now? They're just numbers that represent amounts of red, green, and blue. File permissions, keyboard taps, mouse clicks. It's all just numbers being encoded, decoded, and manipulated 1 bit at a time.
So what this all really means is that even with all the incredible, complex things we do with technology, it all boils down to one single unifying principle. It all shares one common language: data representation.
So from now on, when you look at your screen, remember that you're not just typing words, you are composing a symphony of hexadecimal codes. You're a code talker, speaking the secret language of the digital world. The only question left is, what will you say with it?